Hello guys, my name is Jialu Xing, and it's an honor to present my project here. And my project is about terahertz ryegrass hydration measurement, and it's conducted on the collaboration with the Auckland University Physical Lab, Terahertz Lab, and the Agri Research Limited. And my supervisor is Dr. Dominic Walgott from the Terahertz Lab. First is the project description. And the project is to examine the feasibility of non-destructive determination of relative water content in ryegrass using terahertz spectroscopy. First, I'm going to explain some keywords in it. First, ryegrass is a predominant outdoor feed for grazing animals in New Zealand, so it's quite potential in the agriculture sector. And so for the right side picture, shows the two main breed of the ryegrass, the 150 and the G66. And the relative water content is the proportion of the current water content of a leaf relative to its maximum water content in a fully saturated state, is what we want to measure using the terahertz. And the terahertz spectroscopy is a technique that can use the terahertz frequency electromagnetic waves to non-destructively analyze the structure, composition, and dynamic properties of materials, such as water. So the terahertz will not penetrate water, but it can penetrate the leaves outside materials. So that's why we can use the terahertz spectroscopy to measure the relative water content of the leaves. So, to determine the amount of the water that is contained within the plant and to provide irrigation when the relative water content falls below a certain level is what we really want to achieve. For instance, whenever the leaves, the plant's hydration relative water content falls below the 88, let's say approximately 80%, we'll give them to water and get it back to 96% or so. And here's some literature review about using terahertz beam to measure the water content in different leaves and plants. It has shown that this technique has been studied before, even far to 1996. And we divided our project to the following research questions. And based on these points, we plan to carry out the project in the following order. First is to set up the equipment, which is terahertz source and terahertz detector. And then we're going to use a cuvette water holder to carry out a water layer thickness experiment as a collaboration. And then we're going to study on the thesis on the gravimetric methods, which is a comparison method that has already been proved useful, and to compare it to our method to see if our method is useful. And then we're going to carry out our same experiment on the cuvette water layer thickness, on the broadleaf experiment, and then on the whole plant, which is ryegrass. After all that, we're going to do a system setup in the greenhouse lab in Agri Research, which is located in Palmerston North. So first is about the lab setup. We have two main equipment. They're both from the Terrasons. It's a company, it's a Russia company, but located in America. So first is a terahertz detector. It can capture the terahertz data we're going to use, and the terahertz source, it can generate the terahertz magnetic wave from it. And the setup looks like this. On the left side is a design graph. The source and the detector will be fixed on an optical table, so it will always stay still, and the distance between them will be 25 centimeters, and that's the best distance that can give us the more information. And the plants will be put on a height adjustable holder right beside the terahertz detector in order to get more information. And about the data we're going to use, the data format is a one-channel grayscale data ranged from 0 to 1 in the 32 times 32 n-dimensional array. So each array corresponds to a pixel on the left, And each pixel will have a pixel value at their data. And the data, the bigger the data is, means that the more information of the terahertz are captured on the screen. So that means, for example, if there's leaves in front of the camera, so for the first pixel, if the value is over 0.5, we'll see that this pixel is saturated. So this pixel might have no water on it. And if the pixel is not saturated, so that means the pixel value will be low, like below 0.5, correspond to the blue and black dots on the left side image. So what we want to do is, when the pixel is just unsaturated, we can obtain the maximum amount of information, which is crucial to our experiment. So now let's talk about our first experiment, which is a qubit water layer thickness experiment. This experiment aims to refine our methodology for determining whether the level of hydration the plants we have is feasible. So we're gonna have two groups of data. One is the empty qubit as a reference group and the qubit with water as a sample group. Well, the qubit is a water container with two different thickness, the 2 millimeters and 5 millimeters for holding the water layer. So the empty qubit can be seen at the dry leaves, which the leaves has no water in it, and the qubit with water can be seen as the watered leaves. And our thesis is based on Beer-Lambert law and power loss formula. So in this graph, you can see when the beam penetrates through some certain materials, its intensity will attenuate it from I to I0. So with I0 and the attenuation, we can calculate the intensity before it's penetrated through the material. And on the right side, we can get is the formula we get from Beer-Lambert law and the power loss formula. So with I0, which is intensity after it's penetrated through the material, and this intensity can be achieved from the value from the pixel value. And the dB stands for the attenuation of the source, that is how strong the source are, and the D is the thickness of the water layer, and A is the absorption coefficient of the material, and in these circumstances is the water. So we apply this equation to the reference group and sample group. We can calculate that the water material absorption coefficient from all this data. So we will compare the tested alpha H2O, which is the absorption coefficient, with the one in the literature, which is a constant. And if they are identical, or that means our methodology for assessing the hydration status of the plants is correct. And experiment setup looks like this. We used the laser cut machine in the physical lab to put the qubit holder in it and stick it in front of the camera. And for the reference group, every time we adjust the source attenuation to get the pixels values just not saturated, and adjust the reference group again, and record the present data, and repeat the same measurement on the sample group to calculate the alpha H2O. And our results get is around 50 of the average alpha, which is quite far from the expected alpha. But the good news is we don't have negative values or values that's severely beyond this range. And the result of the qubit experiment was to decide was our primary focus is to change. Is focused on the change in water content that occurs in plants. So we decided to move on to the next step. Next is the thesis on the gravimetric methods. The gravimetric methods is a traditional relative water content measurement method that has already been proved accurate. It's calculated through the weight of the leaves in different status. The W is for the sample fresh weight. The TW is for the sample target weight, which is the weight of the leaf in the fully hydrated status. And the DW is the sample dry weight, which is the weight when the leaves are totally dry. And to measure this, we're going to use a scale to weigh the leaves and put them in the oven to evaporate some water and weigh the leaf to get the current weight, and then put the leaf in the oven to let it dry totally to weigh the dry leaf. And with those data, we can get the relative water content in gravimetric methods. And next, we're going to repeat the same methods on the broadleaf experiment. And the aim of this experiment is to measure the relative water variation of a single leaf with Terahertz method and compare it to the standard techniques. And on the right side is the equation we get previously from the water layer thickness cuvette holder experiment. And just to modify it, and we can get the water layer thickness from all the data we had, the intensity, pixel value, attenuation, and coefficient, the water absorption coefficient, and to get the water layer thickness. And with the water layer thickness, we can get the relative water content through the Terahertz method using the current water layer thickness divided by the saturated water layer thickness, which is water layer thickness calculated in when the leaf is totally hydrated. Ideally, the Terahertz relative water content result and the gravimetric relative water result should show a similar pattern. And then that means we can use the Terahertz method to measure the relative water for the whole plant. So experiment setup looks like this. We're gonna pick up the leaves from Mount Albert Park, and we're gonna put it on a holder, in a metal holder, because the metal won't change its mass due to temperature variation. And we'll put that in the scale, use a 4 decimal precision balancer to weigh it. And when we want to dehydrate the leaves, we'll put the holder and the leaves together in the oven to evaporate under 100 Celsius degree in 4 minutes. And the process looks like this. We're gonna first weight the leaves to get the target weight and take a scan using the Terahertz source and Terahertz beam, and then put the leaf and the holder in the oven to evaporate some water, and do it again to weight the leaves in different status to get more data points, and repeat until the leaf dries up. And here's a comparison image of the leaves when it's still alive and died. And the result looks like this. This is a graph of relative water content against the dry time for the broad leaves. So every time the x-axis is for every time we put in the oven and do a data scan and calculate the relative water content. The black dot is using the gravimetric methods, and the green dot is using the Terahertz method. In comparison to the conventional gravimetric method, this demonstrates that our method of measuring relative water content by utilizing Terahertz data is equally accurate, and the graph shows we have had a good agreement. So we decided to carry on our last phase in the lab experiment, which is the whole plant experiment. This aim is to carry out a procedure that is analogous to the broadleaf experiment to determine the relative water content of the entire ryegrass plant. As you can see, we are putting a pot of ryegrass in front of the camera. And for the experiment setup, because we want to determine the weight of the entire plant after it has been dehydrated, we divided the plant into 2 sections. The section on the left is going to use for a Terahertz data scan, so that part of the plant will be put in front of the camera and do the data scan. And on the right is for the gravimetric data. So every time we're going to do a scan to collect the data points, we're going to cut off some leaves from the right side and weight it for the gravimetric method to do a comparison. So one issue is that it would take a significant amount of time to wait for the ryegrass to dehydrate naturally. Usually take to 1 or 2 days if you put them in a place where there's no sunlight and you don't give them water at all. But we want to accelerate this process, so we make use an oven to rapidly dehydrate the plant at a temperature that would not cause any harm to the plant. After asking for some clues in agri-research, they were recommended to put the whole plant in oven under a degree of 45 degrees Celsius and for no more than 1 hour. In this status, this will not do any harm to the inner structure of the plants. And to determine the target weight, every time we're going to soak the leaf in the water for 3 to 4 hours in total in a water bottle, and while the light and the temperature are the same levels as they are in the common room. Well, at first, when the plants are still not fully dried, this might be effective to get the leaves back to the fully hydrated status. But at the time we put the pots in the oven, gradually damaging its water thickness, water content. So this might not be effective. And that's also one of the reasons why some points in the following charts are not fully aligned. And for the experiment process, first we're going to put the whole leaves in screen to do a data scan. But usually at this time, the relative water content is not 100% because it's actual it's actual plants, whole plants, and we have no idea how to get it fully hydrated. So we're going to cut off some leaves from the plants to do the gravimetric methods measurement. At the same time, we're going to take the terrace data scan and calculate the relative water content from the gravimetric data and the terrace data, and repeat these steps until the whole plant dries up. And when the whole plant dries up, we're going to calculate the terrace relative water content and plot the data together to see if they align. And here's the result. On the left side is the result for the breed 150, and on the right side is for the G66. As you can see, the blue point is the relative water content calculated by terrace data, and the right point is from the gravimetric data. They are quite aligned before the fourth and fifth times of data scan, but on the sixth, some of the red points are quite far away from the blue points. That's maybe due to the plants, the whole plants is already quite dead. They are not vivid as used to be, and we cannot get accurate data from the gravimetric methods because we cannot get target weight. So we're gonna do. So we did another experiment on one breed, and without the gravimetric method, but only on the terrace method to get more points, and focus on the range when the relative water content is 80% to 100%, and we can see still observed quite obvious downward trend, especially from 100% and 65%. And we can see it is clear from the terrace measurement of relative water content holds a great deal of potential, and particularly for the interesting range of 80% to 100%. And last is the system setups in the greenhouse. After all the experiments has completed in the university lab, we have packed all the setups and the data and the Python scripts to the agri-research greenhouse lab in the Palmerston North, and installed the system in their greenhouse and hand over all the work to agri-research crews. Only stayed there for 1.5 days, so I didn't took much pictures of the Palmerston North. The only picture I got is I can give you more is a picture from the airport and the Waitonga sculpture in the nearby forest. Well, it's a lovely city though. The conclusion is it has been demonstrated that the terrace technology is a reasonable and efficient method for determining the relative water content of plants, and it has a substantial potential for future applications in agriculture science. And for the future work, first is additional research and development needs to address the current constraints and improve the precision and dependability of terrace technology for purposing of monitoring the moisture content of the plants, because some of the techniques using the grammatic methods is still not quite precise. And the second and third points are all for the precision of identifying the separate overlapping leaves, which is one of the issues we got encountered in experiments. And without that, using some image algorithm and AI technology might solve that to make the whole precise more precise. And these are the references used in this PowerPoint. And thank you. That's all. Yes.
Just a question, because have you considered this option that during the day when the sun is hot, it might be like this leaves getting dehydrated, but in the evening they recover. It's like standard, I mean, outside, but in lab conditions, how you?
Oh yeah, for the whole plants, like for the one single plants, the experiments were carried out within like 5 hours. It's already fully dehydrated at the end of the experiment. So all the other constraints like weather and pressure and humidity are all the same.
So my point is if you set some kind of equipment that measures like water in the leaves, and it looks like they are dehydrated, you push water, but it like bright sun, and it will damage plants outside. So you probably should consider this also as a factor. Like
yes.
It's not like it's dehydrated and you need to add water at the same moment. Yeah. It might be just plant protects itself from bright sun at this period, but then it recovers later.
Yeah, but that is one thing that should be taken into consideration. But within this phase, first in the lab, university lab, and then in the agri-research greenhouse lab, all the circumstances are identical. So these factors might be quite crucial in the falling status. Like after they have done the projects in the greenhouse lab, they will transfer all the pots and the system to the field in the Christchurch, and they might do the following stuffs and adjustments due to the conditions.
Okay. Thank you again.
Thank you.